now. Trying to get a few. Everything right? Good. We are now. The recording has begun. Now I'll start sharing my screen. Let's see. There we go. All right. So today we're gonna start talking about relations, and I think relation is probably one of the this is like the turning point. Like we're halfway through like the lectures now, right? And I think this is also the point where the material actually starts becoming a lot more challenging than it was before, because some of this. Oh, so I heard something. All right, that wasn't not anything important. So I suggest that, and especially if you haven't mastered the material from 1 through 4, it's going to be very hard to keep up. So I suggest, and this material will, kind of also matter for the next lecture. So I suggest that you probably want to know it very carefully, because a lot of this this material, especially equivalence relation, is very important in analysis and in algebra. All right, so when you think of relation, just in like terms of English, right? You think of like, oh, familial relations or like relationships, right? So you might say, oh, I'm related to my parents, or like I'm related to my siblings, right? And you can kind of formalize that notion using like mathematical relations. So actually, let me just give you the definition. So a relation, right? We're going to say R is between two sets, A and B, is like a subset of A cross B, right? That's basically it. So it's like kind of a rule, right? That tells you which two elements are related in between the two sets, and the subset, right, is going to tell you which elements are related. Okay, so if A comma B, if this pair is in R, right, just subset of A comma B, then we say A is related to B, and you're also going to write A or B to signify the same thing. Okay, but sometimes we don't like to use the letter R, right? So you're going to use this other letter, this sim, right, this tilde, as a symbol for a relation. You can also use other symbols. You can like, basically these are just like kind of like dummy variables or whatever. So you can just use whatever symbol that you prefer. Okay, so and often you're going to let A equals B. What that means is, instead of a relation being between two sets, you're going to have a relation on itself, right? So a subset of A cross A, right? And in that case, we're going to say this is a relation on A. Okay, so as an example, suppose this is a relation on Z, and we'll say that A is related to B if the distance between them is 1, right? So thus tilde, right, is going to be the set consisting of the tuples, or the pairs, x comma x plus 1 and x comma x minus 1, such that x is a member of Z. Okay. Are there any questions so far? Okay, and if we're to continue that, like familial relation kind of analogy from before, you might say, like, if P is like the set of people, right? Set of people, then you might want to say, like, and you say R is like the familial relationship, right? Then you might say, like, me and my mom is in R, right? Something like this. So this, like, so you can take this idea of relationships, kind of, you can make it even more, you can kind of apply it with more constructive things. And turns out this might be important if you're studying like relational databases, for example, right? When you're doing computer science or programming or something. But that's not really going to be interesting for us. So I'm going to bury that and then pretend I never talked about it, because you'll talk about it later if you take a course in databases or something. Okay, great. So now we're going to discuss some what is it? Some properties of relationships, or properties. I don't know if that's the right word. Some types of relationships, let's say. Okay. So we're going to talk about reflexive, symmetric, and transitive, which you should probably remember from, like, let's say, high school geometry. Okay. So, all right. So a relation is reflexive if for any A, right, A is related to A. So, so relation, let's say, tilde, if tilde is a subset of A, comma, A, so these, all right, let me just say this. It's probably best for the purposes of this section, if we're going to say tilde is a relation on itself, a relation on A. Okay. Right. It's just because this thing kind of doesn't work if you have two different sets, right? So if you have, like, for all A in A, we have A is in R, right? Something like this. This is how you would write reflexivity. I'm going to leave it to you, and the other ones are, yeah, and the other relations, it's basically written out. So for an example, right? If the set we're considering is the integers, and we say A is related to B if A divides A, and A and B are integers, right? Then you can see, well, every integer divides itself, right? Well, except for maybe 0. So let's keep, does 0 divide 0? Yeah, sure, because there exists a k such that 0 equals 0 times k. So maybe we can include 0 in here, right? So for every integer, right, then we have that integer divides itself, right? So this relation is reflexive. Okay. As a non-example, all right, if we let A equals the integers again, and we consider all the pairs such that A comma B, such that A is greater than B, right? Well, certainly, right, let's say 2 is not greater than 2, right? So that means 2 comma 2, right, is not in this relation. That means this relation is not reflexive, right? In particular, when you want to show that something is a relation is not reflexive, all you need, right, because this is a for all statement, right? This is a for universally quantified statement. All you need is one counterexample to show that it's not reflexive. Okay. If you have the property that every element is not related to itself, then you say that the relation is irreflexive. Okay. All right. So the next thing is symmetry, right? Or we say a relation is symmetric if for any A comma B, right? If A is related to B, then B is related to A, right? As an example, consider A equals 5. And remember this notation, 5, bracket 5 is the subset of naturals, from 1 through 5. Okay. We have 1 is related to 2 and 2 is related to 1. We can specify a relation like this. This is perfectly valid, right? This is certainly symmetric, right? Because if 1 is related to 2, right, then 2 is related to 1, and that's those are the only relations possible, right? So there's nothing else to check. As a non-example, we have the divides relation we had from last definition, right? Because let's see, 3 divides 6, right? 3 divides 6, but 6 does not divide 3, all right? So this is not symmetric. Okay. And finally, now we're going to talk about the transitivity. A relation is transitive if for any A, B, C, if A is related to B and B is related to C, then A is related to C. Okay. As an example, we have A is equal to Z, that is equal to the integers again. We're going to look at that divides example. If A divides B and B divides C, then A divides C, right? This is something you can easily check. And as a non-example, this example is not transitive because why? Because 1 is related to 2 and 2 is related to 3, but 1 is not related to 3. Okay. Are there any questions so far? Anything in the chat? No. Now, let's see. Do I have space? Oh, sure. So, if you have like a bipartite undirected graph with A plus B vertices, let's say, and you can kind of like think of a relation or a graph, right, as a relation or as like signifying a relation where the vertices, right, is where the set of vertices is the set you're thinking about, right? And then the edges are what defines are basically telling you how these things are related, right? Then if you're talking, you can basically think about a relation on a graph. Basically, that's what this means. If A equals B, then we can talk about a directed graph with just that many vertices instead, right? So reflexivity means that every vertex has a self-fruit loop, and symmetry means that the graph is undirected, because if two vertex, if there is a relation going this way, that means there's a relation going this way. That's what symmetry is. So it means everything is undirected. And transitivity, it's a little bit hard to talk about, but it just says if I'm related to this guy and I'm related to this guy, then this edge also must exist, right? So basically, a chain of edges in your graph induces another edge. Okay. So let's see. I think I should have time. So let me give you something. I want you to think about this for a moment. Okay. I want to show you, right? I'm going to claim that symmetry and transitivity imply reflexivity, right? And the idea is simple. Okay, if X is related to Y, right? Then symmetry implies that Y is related to X, but transitivity now implies, right? Symmetry. My transitivity implies X is related to X. So we have reflexivity, right? Does that make sense? Or does that not make sense? Maybe I'll give you one more minute to think about it. Or does anyone need me to repeat that? Is anyone there? Oh, it makes sense, does it? Oh, there's another question. So like in a graph, it would be a complete undirected graph with 3 vertices. So if you have all those 3 things, then yes, it probably would be a complete graph, right? Rajiv thinks this my argument makes sense. Justin, do you agree? All right, that's wonderful, because this proof is wrong. No, it's not true. And maybe as an exercise, right? You'll see a related exercise. Think you'll as one of your homework exercises will basically have you think about why this is not true. Okay, but this proof is wrong, right? And I thought it was, and for a moment or for like a few hours, I thought this was true, but this is not true. It's not true. So maybe what I just told you, symmetry and transitivity do not imply reflexivity. Does that make sense? Or this proof is wrong. So I'm going to and it's going to be basically part of your homework to think about why this is wrong. Okay. All right. But so that means all these three. But let me maybe pause here. I think because I think we still have some time. Is everyone okay? In the absence of any objections, I'm going to move on. Okay, I'm going to move on. So that just basically tells us all these three. So the next thing we're going to talk about is an equivalence relation, which gives us a notion of how things are equal in a set, right? Other than the boring old equal sign, right? And an equivalence relation is any relation that has the three properties that we just discussed. It needs to be reflexive, symmetric, and transitive, right? You can just remember them as RST because it starts with RST and there are consecutive letters. I guess you can use this. And while the argument from before might just imply, hey, why do we have reflexive? Didn't we just say that symmetric and transitive imply reflexive? But it's not really the case. You actually do need all three properties. Okay, they do not imply each other. And one important equivalence relation that comes up in algebra and in number theory is this what is it? The congruent modulo n relation, which right now will denote as the 3 bars, which is backslash equiv with a subscript n, modulo n, right? Which it is basically all the pairs a comma b such that of integers, right? Such that n divides a minus b, and n is given. All right. So we say a and b are related if n divides a minus b. Okay. Many times, many sane people will use the other notation, congruent and something, and mod n, right? So you say a is related to b mod n, and you say a is congruent to b mod n. Okay. So this is it's easy to check that this is an equivalence relation, right? Because a minus a is always 0, right? So it's reflexive. So anything divides 0, so it's reflexive. Symmetry is also true because if a minus b is divisible by n, then b minus a is also divisible by n. And transitivity is also true because a minus b plus b, a minus b, wait, if a minus b n divides a minus b and n divides b minus c, then a minus b plus b minus c is divisible by n, right? You can write this out formally, but I'm just going to give you like a very short argument. Okay, so let's, for the sake of example right now, let's just look at n equals 3, right? Then you say 0 is congruent to 3, is congruent to 6, is congruent to 9, etc. And because a relation is transitive, right? I just told you that it's transitive. All of these things are related, right? So 0 is related to 6, right? 3, 9, you can basically go in any order you want. And the same happens for 1, 4, 7, 10. And you also have 2, 5, 8, 11. And you kind of see, you're kind of seeing that every integer is related in here, right? And no integer, and if 0 is related to 3, right? And 0 can't be related to 1, right? So excuse me. So you kind of have this like chain, like 3 different chains of equivalences, if that makes any sense, right? So there is something interesting going on here, and to talk about that, we're going to go to the next definition. Oh, well, is everyone okay with me so far? Is everyone with me?
Yeah, sounds good.
Steven, you don't really count.
Okay, I'm sorry.
All right, so the next thing we're going to talk about is a partition. Okay, because what is a part? So you probably talked about partitions already, since you all took calculus and you talked about partitions probably in terms of Riemann integration, right? Now we're going to actually formalize that notion. Although like in books, the definition of partition given is specialized towards that specialized towards the construction of the Riemann integral, so it's slightly different. But right now we're going to talk about partitions of a set. Okay. So what is it? It is a collection, right, of a non-empty set. We're just going to say it's not empty because we don't want to talk about empty sets. A collection is a collection, curly A. Usually when you talk about collections, you use like the calligraphic font. It would be mathcal A of subsets of A, right? Satisfying these three conditions, right? You have the empty set is not in the partition, right? And if there's P and Q, if there's two sets in the collection that are not equal, right? They're different. Then they must be disjoint, right? And the union of all sets in this collection must be equal to the whole set. Okay, does that make sense? Did this definition kind of make sense? Great. And now if you go back to this example over here, these sets that we have is going to construct a partition because the empty set. Well, let's actually take a look at the next proposition before we discuss this. Okay, so there is a one-to-one correspondence between partitions and equivalence relation. Well, is there? Actually, I don't know. You're going to have to think about that actually. So an equivalence relation on A, every equivalence relation induces a partition on A. Okay, so two elements are in the same partition exactly when they are related. Okay. So let's do this. So let's tilde A be an equivalence relation on A, and consider the sets A sub A. Maybe that's not the best notation. Defined such that all x in big A such that x is related to little a. Okay. Then for any A and B in big A, where A is related to B, then we want to show that A sub A is equal to A sub B. Okay. If x is in A sub A, that means x is related to A. But since A is related to B, that means we have x is related to A and A is related to B. Then we have x is related to B, right? So x is related to B. That means x is in. So that means x is in A sub B, right? And symmetry just shows that the other direction is true, right? So that means you have the other reverse containment. So that means A sub A is equal to A sub B if and only if A is related to B. Okay, does that make sense? Okay, I'm going to assume that made sense. All right, so now we're going to construct, let curly A, right, be the collection of A sub A, right? So notice that, so now you want to show that this is a partition. The empty set is not in this collection because if A sub A is in curly A, right, then this has got to have an element in it, right? Because little a needs to be in this particular set because A is related to itself because it's an equivalence relation and everything is reflexive, right? Okay, now pick some A sub A and A sub B. Suppose that there is some x in their intersection, right? Then x is related to A and x is related to B, but we deduced, right? But this means that A is related to B, and that means, and from our discussion earlier, that means A is related to B. So that means these two sets are equal. Okay, so that means That means there are no two distinct sets in curly A with non-empty intersection. Finally, every little a in big A, right, needs to appear in at least one, right? And it's in particular, each a is for every a in, or let's say x, for every x, right? If x is in A, right, that means x is in A sub x, right? So that which is in curly A. So that means this union must contain A, all right? And since this union was comprised of subsets of A, that means you have set equality. Does that make sense? Is that okay? Okay. I'm going to assume that this was okay. So now, if we go back, right, we said, what did we say? We said, oh, by the way, one more piece of definition. We refer to each A sub A above here as an equivalence class, right? Okay. So from our discussion of like congruence modulo n, right? We have that this modulo relation, congruence modulo n generates, or modulo 3 generates 3 equivalence classes, right? You're either 0, 1, or 2, basically. And that means you can form a partition of Z, right? That means we can form a partition of Z. And I think, what is it? Someone said in the Discord, like I think a week ago, said, can we use the fact that every integer is even or odd? And Adam said that, like, well, you technically don't, technically you need to prove it, but you can just use it as given for that problem. I don't remember which problem it was. Well, now we actually have the tools to prove that particular proposition, right? Because even or odd, right, is congruence modulo 2. And that is an equivalence relation. And that means it induces a partition on Z. In particular, one of the sets would be the odd integers, and the other subset would be the even integers, right? So that would mean that that would show that every integer that you have is either even or odd. Okay, so now that we have the tools, and now we actually have the tools that we want. Okay, is that okay? Great. Okay, cool. Right, and in general, right? Right, everything in an equivalence class is related, and every pair of things in two different equivalence classes is not related, right? In general, this congruence modulo n generates n different equivalence classes, and we call the set of these equivalence classes under this this relation to be z sub n, or z mod nz. This notation, right, is used to denote like something like quotients via a equivalence relation. But you will and you will see this notation more when you take a course in abstract algebra. Okay. And for ease of notation, we give each equivalence class as a representative element, right? So if you say if you have m in A, right, then you would have A sub m, right? You would also write bracket m to denote the equivalence class of m, and you would if any like different letter, or let's say if n is related to m, you would kind of count them, and in this equivalence relation, you would count everything as the same, right, under this equivalence relation, as in that, like, if n is in m, right, is in this equivalence class, you would kind of do operations pretending that n is equal to m. Other notations that some people use is just to put a bar over m, which has the advantage of being less strokes or fewer strokes than the brackets. Okay. Does that make sense? So why do we care about equivalence classes? And why do we care about these representative elements, right? So we might want to, so when we define the notion of like this quotient, right? Basically modding out, and like defining an equivalence relation on them, like it gives us a way to define which elements are equal, right? As I said, and furthermore, it gives us a way to define functions and operations on them. So here's this. Let me give you an example. So in Z3, we can define addition similarly as in Z, right? We're going to be adding equivalence classes together, right? But the problem is, right? But the problem is this is just like this plus operator, right? And we're using this plus operator, and we usually use them for numbers, right? But on the other hand, these things we have over here, these are sets, right? Because this is a set, right? In Z3, it's all the set of, I don't know, what letters do I have? Let's say K in Z, right? Such that, what is it? K minus N 3 divides K minus N. What am I saying? Such that 3 divides K minus N, right? So this is set, and now we're talking about adding two sets together and getting a different set, right? And so you might be wondering, is this well defined? Well, and you can kind of, and you might be, well, actually no. The first question we should ask is, how do we define an addition on sets like this, right? And when we have this equivalence relation type of thing. And turns out there's like a very natural way to do this, right? Just add n plus m and consider the equivalence class of that, right? But when we do define this, the other thing that we need to check is that we need to check that it's well defined, right? And when we say something is well defined, what we need to do is we need to check that this operation doesn't depend on the choice of representative, right? How can we be sure that if we have two different guys in this equivalence class, right, that n1 plus m and n2 plus m are both in the same equivalence class, and they basically they come out to be the same thing in when we mod out everything via equivalence classes, right? And that's something that we actually need to check when you're trying to define these operations in equivalence classes. Right? If you have n prime and m prime in the equivalence class of n and m respectively, right? Then because n prime minus n divides k, 3 divide by definition, so n prime is equal to 3k plus n, and m prime is equal to 3l plus m for some k and l and z, right? Then you have n prime plus n prime plus m prime is equal to 3 times k plus l plus n plus m, which shows, and this shows, right, because that n prime plus m prime is in n plus m, because this just shows that what is it, n prime plus m prime, right, minus n plus m divides 3, or 3 is divisible by 3. 3 divides, sorry, right? So that shows that this operation is well defined. Okay. You can check that. You can construct like an addition table using this operation. And when I say operation addition table, I mean, you can just say 1, 2, 3, 1, 2, 3, similar to how you constructed multiplication tables in grade school. Okay. And analogously, you can also define multiplication in Z3. And it is exactly what you would expect. The equivalence class of n, right, times the equivalence class of m is equal to the equivalence class of n times m. Okay. All right. So did this discussion make sense? Basically, the point did I say 0, 1, 2? It's 3 is equal to 0. I don't care. Yeah. Oh, when did Adam get here? Hi, Adam. No one else came. No one else came. um. So one way equivalence classes are useful is the idea you can define quotients, and you can define operations and now functions on quotients. Okay, and this idea will become very important when you take a course in abstract algebra, as I said before. Okay, does that make sense? Before I move on, because that's basically going to conclude our discussion on equivalence classes, except for this one little blurb. The graph representing an equivalence relation is a bunch of complete graphs together. So because if you have like an equivalence class, right, then we're going to well does a complete graph, I forget, does a complete graph have self loops?
No, that would be weird. Complete graphs are simple graphs.
So right, so maybe let's just think about this on your own time, because I don't like graphs. I don't like graphs. I think Adam alluded to that last lecture, but I don't like graphs. I don't like graph theory. So I'm going to leave this to you to think about and discuss on the Discord. Great. So this concludes our discussion on equivalence relations. So let's move on to the next thing. Now we're going to talk about order relations. We say that and here's our next definition. We say that a relation is antisymmetric if for all A not equal to B, either A is not related to B or B is not related to A. Okay. We have this, but I like to think about the antisymmetry in the contrapositive, right? Which says for all A, B in A, right? It says, let's see, what's the A related to B and B related to A, right? This thing implies A equals B. Okay. This is how I would think about it in the contrapositive. I think this is probably a little bit more useful when you are proving things. Great. So what is a partial ordering? That's the first thing we need to talk about. A relation is a partial ordering if it's reflexive, antisymmetric, and transitive. So we took the symmetry relation from equivalence relations and we replaced it with antisymmetry, right? So and the note here says that a partial ordering should be thought about like its name implies. It orders elements in some sense, but it's not always true that for any A comma B, one of them is always larger than the other. In that sense, it's only partial, right? If a partial order has the property that any two elements that can be in the set can be compared via that partial ordering is called the comparability property. And if a partial ordering does have the comparability property, then we say it as either a total order or a linear order. And you will think about this. There's a homework problem relating to total and linear orders. So let's look at an example, right? An example of a partial ordering is like the usual order, right, on N or Z or Q or R, right? And since we have time, excuse me. And while I said that it's easy enough to check this, we have some time left over. So let's actually check that this is true. So first of all, if let's restrict ourselves to Z, because I don't want to think about R or anything too complicated. So I'm sure every proof will fall through anyway. So for all x and z, right? X is less than or equal to x, right? Because x is equal to x. So this is automatically true. Nothing too interesting going on there. Next, let's see. Next, if x, let's say x and y are in z, right? If x is less than or y, and y is greater than, that is not what I wanted to write. That is not what I wanted to write. And x is greater than or equal to y, then this means that x is equal to y, yes? Simple enough. And x less than or equal to y, and y is less than or equal to z, implies that x is less than or equal to z. Nothing too interesting going on there, right? So that means, so this shows that, so we verified all three properties, and so this relation is a partial order. Okay, great. And the other canonical example that I want to discuss, right, when we discuss partial orderings, is the subset relation on the power set of A, right? We're going to show that this is a partial order, all right? So if for any subset of A, right, that is, it's a subset of itself, right? So that means our relation is reflexive. Next, if we have two sets, right, two subsets of A, such that X is a subset of Y and Y is a subset of X, well, this is exactly the criterion for determining if two sets are equal, right? So X is equal to Y, and that verifies anti-symmetry. And finally, if you have X is a subset of Y and Y is a subset of Z, then X is a subset of Z, right? That shows our relation is a partial order. And this example is a partial order, right? It's not a total order like the other this example. Because why? So if we're considering, let's say if we consider well, no, because not every subset can be compared to another one, right? So let's say if our set is Z, right? If we're considering Z, right? You have this 1, 2, 4, and a set 1, 2, 3, right? Neither of these sets are subsets of each other, right? So you don't really have so we can't. There is no way to compare these two elements together. Right? But so it's not a total order, so because it doesn't have the comparability property. But it is a partial order, like we said. Okay. Is that okay? Oh, Adam is gone. Is that okay with everyone?
Sure thing.
All right. Wonderful. So what's an and it turns out I probably should have given an example of something that is not a partial ordering. But I didn't and I failed to do that. What would be a good partial order? I think, let's see. Well, any one of the examples that we had above, if you have something that's not reflexive, like this one is an order relation, right? But it's not a partial order because it fails in our definition in the sense that it's not reflexive. I guess, yeah, I guess the modulo relation, modulo n, is, I don't think that's a partial order either. In general, equivalence relations, I think, are different than partial orders, but I might need to think about that a little bit while. Okay, so when you have these partial orderings, right, you might want to think about remember when we had like this we gave you this symbol. We told you to think about this as the analogs, less than or equal to, and then less than sign, right? And if these two are partial orders, right, then we probably want a name for these types of relations, and this is exactly what we're going to give you now. A relation is a strict partial ordering, right? If it is irreflexive, antisymmetric, and transitive. And it turns out I didn't write down irreflexive in the notes, so I'm going to write down what irreflexive means. Irreflexive, a relation is irreflexive. Well, you can probably guess, right? If for all x in A, let me say on A, x is not related to x. Okay? And just as we verified that the less than and the proper subset relation, just as we verified that the less than or equal to relation on these numbers and the strict subset relation on the partial and the power set of A are strict partial orders, or are just, what am I saying? It's just as we verified these two are just regular partial orders, it's fairly easy to verify that the less than relation and the proper subset relation are strict partial orders, right? And the only thing to verify is irreflexivity, because we verified antisymmetry and transitive. Okay. All right, we're almost done. Somehow. Is there anything else? Is there any question so far? Okay, I don't think I see a question. Okay. So the next thing, now we're going to talk about upper bounds. So let A be a non-empty set, and let this be a partial order on A. This symbol is denoted prec for preceding. If B is a subset of A, right, then we say that any alpha or an alpha in A is an upper bound for B if B is ordered before alpha for all B in B. Okay? And furthermore, if alpha has the property that alpha is less than beta for all upper bounds for B, then we say that alpha is a least upper bound for B. Another word was the supremum of B, and we would write alpha is equal to sup B. Okay? And then if alpha, if the supremum is contained in the set, then we say that alpha is the maximal element, or the maximum of B. So this is like a gigantic definition, right? It's pretty thick. So maybe so maybe you need like a moment to think about it, and I'll give you like a moment.
Are we considering like sets that could have, or that could be like infinite, like have infinitely many elements or something?
Sure. Yeah. Yes, you can. Yes, you can. For example, if we have A, I don't want to give you that example.
Like real numbers conversion to some number, then like the
you can
would be that number.
You
that
can
they
consider
converge.
real numbers. So if you have, let's say we have R
1 minus 1 over n or something like that.
Oh, I was going for, yes, but you can think about 1 minus 1 over n. The supremum, sure. If the example that was just discussed is the set, let's say right? The set 1 minus 1 over n such that n is in the natural numbers, right? And the soup, let's say this is A, then the soup of A is equal to 1. And this certainly has infinitely many elements. All right? Does that make sense?
Yeah.
Or if you just say, like, let's say we're considering the power set of n, right? Under the subset relation, right? Then the supremum, the maximal element, right, is just n, right? Does that make sense?
Yeah. And also,
Mhm.
for what is it? So for strict partial ordering, it would be impossible. Well, there would be no maximum of B, right?
There will be no maximum element, right? Because it would need to be you would need to be able to compare
Indeed.
that to itself, right? And that's not necessarily true. Good. Is there anything else? Right. So lower bounds and greatest lower bounds, right? And for that we give the name infimum, or just say int b, are defined similarly, and we will not discuss it, and we will not really discuss it because we really care more about soups and upper bounds for some reason. I don't know why. Okay. So let's think about an example. Consider A, right, be equal bracket 5 as a subset of Z, and under the usual less than or equal to order. And we can see that 6 is an upper bound, right? Because what did I write here? What the heck? That should be a 5, not an n. Right? So 6 is an upper bound for A because for any guy in this set, 6 is less than, or 6 is greater than, right, or equal to everything here, but it's not the least upper bound, right? And 5 is the least upper bound for A. And so 5 is in here, and it is a maximum, right, of A. As another example, consider the power set of 5 under the subset of relation, and if you have Q to be the power set of 5, right, minus 5 itself, right, then 5 itself is the least upper bound of Q, right? Because for all subsets of bracket 5, bracket 5 is a superset of every subset of bracket 5, right? And there is in fact no other upper bound, right? So it has to be the least upper bound. And of course, there are sets where the least upper bound just does not exist. Okay. We're actually going to return to this idea in a later lecture when we discuss the real numbers and the axiom of completeness. Are there any questions? That is basically the end of what we prepared. So I might as well talk about what I promised last, or what I seem to have promised in lecture 5. Are there no questions? Oh, wait a minute. I can wait a minute.
I guess this is more of a convention question, but when
Sure.
we're comparing like real numbers, is like less than or equal to generally, like the standard ordering, or is like just a normal less than sometimes used?
I mean, no, this is not a question. Like, I don't know.
Or is like not like something that is not
It's
like
not
meaningful?
something that like you really think about, because
Oh, okay.
you can just, everything's just the same thing. You know what I mean? Like
Yeah.
a lot of the things you can do with less than or equal to, you can do with less than, and a lot of the times actually it's just going to depend on the book. And actually I think, yeah, it'll just depend on the book, I think. I think I saw less than more often, though I'm not really sure. But I think it really depends on the author, because some books use less than, some books use less than or equal to. But I think generally you probably want to deal with open sets, right? So you probably want to deal with less than, I think.
Okay.
I don't think I see any other questions or objections. So I'm going to talk about what I promised you last time. And when I say I promised to you, I'm talking about the well ordering theorem. So what did he say? So we said, right, a partial order is a total order, right? If it has the comparability property, that means let's say this is a partial order on, let's say, A. That's not supposed to be a curly A. That's a regular A. All right. If we say it as the comparability property if for all A and B in A, either A prec B or B prec A, right? And then if you have this, then we say it is a total order or a linear order. Okay. Now we say that's a set. We say that a partial order, right? And we say actually, and if we a set and and a I guess we never really said this in the notes, right? This is a partially ordered set, right? This pair ordered set, and you can, in fact, you can call it a poset for short. Sounds weird. For short. Right. Okay, and we say that a partially ordered set has the well ordering property, right? If every subset, right, under this relation has a minimal element, right? And you saw that this is true with the natural numbers with the well ordering principle, right? Recall that the well ordering principle says every subset of n has a least element, right? Do you recall this? When you did graph theory and stuff from last lecture? Well, under this relation, right? Under the regular thing, but and we alluded to the well ordering theorem, right? Which says every set, right, can be well ordered. And this, it turns out, like, was very controversial when it was first like published in like the early 20th century. I think it was Cantor who said this was like an undeniable truth or something. I think Cantor said did Cantor publish this without proof? I don't remember the exact history of this, but this is like very non-intuitive, right? So how can you think of a well ordering, right? You need to be able to can you think of a well ordering on R, right? Well, certainly the usual order doesn't work, right? Because not every subset has a least element. But there must be some different way you can order all of these elements such that every subset has a least element. And this is very, you might be able to, you might be able to kind of construct one for Z, right? And in fact, you might even be able to construct a well ordering for Q. I think if you use the fact that they are both countable, which we'll get to in 2 lectures. But for R and for C, right? For these sets and for any set that might be very wild and crazy, there is always a well ordering. And this is very non-intuitive, right? And in fact, this is equivalent to the axiom of choice. The axiom of choice, and what does that say? It basically says that if you have a bunch of sets, if you have like a collection of sets, right, there is a choice function, which basically says that you can pick out an element from each set of the from each set in the collection. And while this is very intuitive, especially for finite sets, but when you like go into the realm of infinite sets, you'll find that it's very non-intuitive. And it turns out that the well-ordering theorem is equivalent to the axiom of choice, right? And to prove the well-ordering theorem from the axiom of choice is very non-trivial, as you might expect. If you want to do it directly, I think it requires transfinite induction, which we do not cover in Math 300, or I don't think any iteration of Math 300 would cover transfinite induction. If you want to talk about transfinite induction, you would probably need to take the set theory course. But there is a different way you can prove it using Zorn's lemma, which is also equivalent to the axiom of choice. Right, and to talk about the well-ordering theorem implies the axiom of choice. Well, you can just say that like if you have each subset, right? If you have each set in the collection of sets, well, you can just say make the choice function be that just take the least element, and that'll basically imply the axiom of choice. So that I don't think that direction is too hard, but the other direction is fairly harder. Okay, so but so that was just basically like a I guess what I promised you from last lecture. Some cool stuff that's going on in there. Are there any other questions? Well, by the way, none of the stuff that I talked about will be relevant, I think. Or when I say relevant, you don't need to know for the homework and probably not the proficiency exam. Yes. Because the axiom of choice can be very non-intuitive. Are there questions or objections? I'm going to stop presenting. Okay, in the absence of any questions, I'm going to stop the recording.